It's just after midnight on December 17th, 2016, at the Pivnichna substation outside Kyiv. Breakers begin snapping open, one after another, in a rhythm too fast and too even for human hands. No one in the control room is clicking anything. No one needs to. A year earlier, an almost identical outage in Ukraine had taken a team of attackers sitting at keyboards, clicking through hijacked screens for hours, one breaker at a time. This time, the only thing doing the clicking is software, a program built to speak the substation's own control language, running on a schedule with nobody at the controls when it happens. This is the story of Industroyer, also known as CrashOverride. The moment attacks on the power grid stopped needing a human hand to carry them out. Failure Mode, Episode 3. Industroyer, also known as CrashOverride. Two research teams found it independently and gave it two names. ESET, the firm that first tore it apart, called it Industroyer. Dragos, the industrial security company that analyzed it in parallel, called it CrashOverride. Same malware, two names, a pattern this channel has seen before. What both teams agreed on was what it was: a modular attack framework built to operate electrical substation equipment directly, not by exploiting some hidden flaw in it, but by speaking the equipment's own native languages fluently enough to give it commands it had no reason to refuse. The story of how that framework came to exist starts a year earlier, with a smaller, cruder attack on the same country's power grid, one carried out by hand, by people, clicking through stolen access, one breaker at a time. This episode is about the distance between that and what came next. How a small team that had done this once, manually, built something that could do it alone. To understand why Industroyer mattered, it helps to understand where in the grid it was aimed, because that target was different in kind from the one hit a year earlier, not just in scale. Most people's experience of the power grid ends at distribution, the local substations and lines that make the final delivery to homes and businesses, the last mile. The 2015 attack, which this episode covers shortly, hit exactly that layer. Regional distribution companies, the point closest to the customer. Transmission is a level up. It's the bulk movement of high voltage power between generating stations and the distribution networks that then fan it out to customers. Pivnichna, the substation Industroyer hit in 2016, operated at 330 kilovolts, a transmission class voltage, not a distribution one. A transmission substation typically feeds multiple distribution networks downstream of it. Open one breaker at that layer, and the effect ripples through everything relying on it below. A wider footprint per action than switching off a single distribution feeder to a neighborhood. To actually operate that equipment, Industroyer needed to speak the languages substation hardware uses to talk to control systems. There were 4 of them built into the framework, each as a separate swappable module, i.e. C608705-101 and IE C608705-104, a pair of related protocols common in European grid equipment, IE C6185. A newer standard used in modern digital substations, and OPC data access, a general-purpose industrial communications standard used to talk to systems like ABB's microscaler. In plain language, these are the vocabularies substation breakers and control systems use to understand instructions from a controller. They were designed decades ago for closed, trusted networks on the assumption that anything speaking the protocol correctly was supposed to be there. None of them ask for a password. None of them check who's asking. That design assumption is exactly what Industroyer relied on. And it's worth being precise, about what that doesn't mean. The four protocol modules don't rely on a software vulnerability in any ABB or Siemens product, and they don't use a zero-day exploit. They open breakers the same way a legitimate operator's software would. By issuing valid commands in a protocol, the equipment was built to obey from a position inside the network the equipment already trusted. That's the entire trick behind this part of the attack. Not breaking through a floor, but walking up and speaking the native tongue fluently enough that the equipment had no reason to refuse. What made the framework dangerous wasn't a single clever exploit at all. It was the architecture around it. Industroyer was built as a core backdoor with swappable payload modules bolted on, one per protocol family. Point it at a substation running IEC 6185 gear, load that module. Point it at one running the older IEC 608705 protocols, load a different one instead. The same core framework could, in principle, be re-aimed at grid equipment from other vendors or other countries just by changing which module it carried. No rewrite of the whole tool required, and no self-spreading mechanism needed to reach a new target. To be clear, Industroyer is not a worm. It doesn't propagate on its own, from machine to machine. Its danger and its reusability come entirely from that modularity. A framework built once, then re-equipped for the next job, the way an attachment gets swapped onto the same tool rather than the tool itself being rebuilt. That's the shift this episode is really about. In 2015, hitting a new target meant a team of people learning the target's systems and clicking through them by hand, one screen at a time. In 2016, hitting a new target could mean something much smaller, swapping a module. To see how big a leap 2016 really was, start with what came directly before it. December 23, 2015, roughly a year earlier, the direct predecessor to this attack and the baseline everything in this episode gets measured against. Attackers using the malware family Black Energy 3 alongside a destructive component called kill disk spear-fished their way into the corporate networks of 3 regional Ukrainian distribution companies. From there, they didn't need anything as sophisticated as Industroyer. They found legitimate remote access tools already installed and in daily use on those networks, and used those same tools to work their way from the corporate side into the utility's own operator software. And then they did the attack by hand. Sitting at hijacked HMI sessions, the same screens a real operator would use to run the grid, the attackers clicked through breaker controls themselves, substation by substation, opening them one at a time. It was slow, deliberate, manual work, done live, in real time, by people watching the same interface a legitimate operator would be watching. Across the 3 companies, this took out power to roughly 230,000 customers, with outages lasting between 1 and 6 hours, depending on the location. It wasn't only technical. While breakers were being opened, a flood of junk calls hit the utility's telephone call centers, tying up the lines customers would have used to report the outage. A low-tech complement to a hands-on keyboard attack meant to slow the human response on the other end, just as the attack itself depended entirely on human hands on this end to carry it out. Once the breakers were open, Kill Disk wiped data on affected systems, destroying logs and making recovery and investigation slower and harder. It worked, and it was disruptive. The first confirmed cyber attack to cause a power outage anywhere. But every part of it depended on people. People fishing their way in. People finding the remote access tools. People clicking the breakers open one by one for as long as it took to work through 3 companies' worth of substations. That labor-intensive, hands-on keyboard method, skilled but entirely manual, start to finish, is the baseline the following year's attack would leap past. 1 year later, on December 17, 2016, the same country's grid was hit again, and almost nothing about the method looked the same. The target this time was a single substation, Pivnichna, a 330 kilovolt transmission facility outside Kyiv, one layer up the grid from the distribution companies hit in 2015, and a single site rather than three. Sometime around midnight, a payload already sitting inside the substation systems executed on a schedule. Nobody logged in to trigger it. Nobody was watching a screen and clicking a button to make it happen. It simply ran. At the time, it had been set to run. Rather than hijacking an operator's session, the way the 2015 attackers had, the malware spoke to the substation's own control equipment directly in its native protocols, the industrial languages described earlier in this episode. It issued the commands to open breakers itself, translating them into the exact protocol traffic the equipment expected to receive from a legitimate controller. Breakers opened in sequence, without a human clicking through a single one of them. The outage that followed lasted around 75 minutes and cut power equivalent to roughly a fifth of Kyiv's electricity consumption during that particular late-night window. Not a fifth of the city's population, not a fifth of an ordinary day's usage, and nothing about Ukraine as a whole. Just the load that one part of the grid happened to be carrying at that hour. Set the two attacks side by side, and the contrast is stark. In 2015, a person had to be at a keyboard, clicking through screens for every single breaker across 3 companies for as long as 6 hours. In 2016, one piece of software opened breakers across a single, higher voltage substation in about 75 minutes, and no one needed to be at a keyboard for any of it. The framework also carried components aimed at more than simply opening breakers. One was a data wiper, similar in purpose to Kill Disk the year before, meant to destroy files and complicate recovery and investigation afterward. Another was built around a known denial of service flaw in Siemens Ciprotec protection relays, hardware whose job is to automatically trip and shield equipment from damage during abnormal conditions. That flaw, tracked as CVE 2015-5374, had already been publicly disclosed the year before the attack. It wasn't a secret, and it wasn't a 0-day. The apparent intent was to use it to disable that protective layer, so that when engineers rushed to manually restore power afterward, the safeguards that would normally prevent equipment damage during restoration might not be there. It's important to be precise about what this means. The evidence points to intent to enable damage during manual recovery, not confirmed large-scale physical destruction. The attack was detected, and power at Pivnichna was restored manually within hours, with no confirmed record of lasting equipment damage from this particular incident. That combination is what made 2016 different in kind, not just in scale. A single scheduled execution, no hands on the controls during the breaker opening itself, speaking the grid's own languages to move breakers directly, with a wiper and a relay disabling capability riding alongside it, aimed at making any human response afterward slower and riskier. In the weeks that followed, 2 research teams pulled the malware apart independently. ESET, which analyzed it first, named it Industroyer. Dragos, working in parallel, named it CrashOverride. Same piece of malware, 2 names from 2 teams. The same pattern this channel saw with Triton, also tracked by some researchers as Hatman. Attribution followed a similar shape to that earlier case too, though it points to a different actor. Multiple governments and private researchers have assessed both the 2016 transmission substation attack and the manual 2015 distribution attack that preceded it as the work of Sandworm, a unit of Russian military intelligence tracked elsewhere as GRU Unit 74455. That distinction matters. This channel already noted, covering Triton, that the group behind that attack was not Sandworm. Sandworm is a separate actor with its own toolset and its own track record, now attached to both Ukraine grid attacks. And as with Triton, it's worth being precise about what attributed means here. Multiple governments and independent researchers assessing an attack as Sandworm's work with high confidence is not the same thing as that link being proven in a court of law. The assessment is strong. It is an assessment, not a verdict. What the aftermath didn't include was a repeat performance, at least not right away. Industroyer was deployed once against one substation, and then the framework went quiet. It didn't disappear though. It went back into storage, which turns out to matter a great deal later. A few things are worth carrying forward from this one. First, automation changes the economics of an attack. A skilled team clicking through hijacked screens by hand, as in 2015, is a one-time achievement. Repeating it against a new target takes that same team and that same effort all over again. A reusable framework, built once and re-aimed by swapping a module, doesn't need that team back. It needs someone to load the right payload and set a schedule. That is the practical difference between a skilled act, performed once by people who know how, and a weapon that can be handed off and used again without them. Second, the industrial protocols underneath a great deal of the world's grid equipment were built for trusted, isolated networks, places where anything speaking the language correctly was assumed to belong there. That assumption becomes a liability the moment an attacker reaches that network, because the protocol itself has no concept of a stranger. It was never designed to say no to anyone who speaks it correctly, and that is true of this equipment across vendors and across countries, not just at Pivnichna. Third, Industroyer's modular design, a core framework with swappable, protocol-specific payloads, isn't some exotic attacker innovation. It's ordinary software engineering, the same logic behind any product built from interchangeable parts. That's precisely what makes it worth taking seriously. The same modularity that makes legitimate software easy to maintain and adapt is what makes an attack framework easy to retarget at scale against equipment far beyond the one substation it was first used on. Industroyer was used once against one substation, and then it went quiet. Quiet isn't the same as gone. In April 2022, a new sample surfaced, aimed at a Ukrainian energy company. Researchers called it Industroyer. It shared source code with the original, specifically a module built around the IEC 608705104 protocol, the 104.dll component. Concrete evidence that this wasn't a copycat, but the same framework, kept for 6 years and brought back out. Where the original had carried 4 protocol modules, this version carried a single, narrower one, a smaller, more targeted rebuild of the same tool. This time, it didn't work. ESET and Ukraine's CERT-UA caught it and blocked it before it could execute. No breakers opened, no blackout followed. A framework built once doesn't have to be used only once. And getting caught on one attempt doesn't mean it won't be tried again. Subscribe for what happens next time a framework like this one resurfaces.